Hello everyone, today we're going to look at the tan function. Before we jump into the sketch, I wanted to show you guys what this looked like. And you can see it kind of looks like a series of cubics where it has these asymptotes down this line here, and they're going to occur periodically. The reason we have asymptotes with tan functions is because tan is sine divided by cos. So wherever cos is 0, I get division by 0. So I wind up with an asymptote. If here is pi, here's 0. You can see smack bang in the middle, it's going to be pi on 2. We know cos is 0 at pi on 2 or negative pi on 2. So that's our tan function. In terms of what we're going to include, there's slightly less than the trig graphs because in this case, we don't have the same, or sorry, not the trig graphs, the sine and cosine graphs, because we don't have the same kind of cyclical nature of those functions. However, we do have where our roots are, and we say these roots occur every n pi. So you can see, at n0 it's 0, positive 1, positive 2, positive 3, and obviously it goes negative as well. If I change my period, if I make this 2, it now is going to halve the distance between those roots. So 0, now it's pi on 2, then it's pi, 3 pi on 2, then it's going to be 2 pi on negative 3 pi on 2, negative 2 pi. So we can see here that if I change the period, it essentially just brings those middle points a little bit closer by whatever the factor is that I add here. We do need to find our x-intercepts though with our trig graphs. You can see we get some nice pi values. We can do this either with our exact values by kind of solving this equals 0, for example, or we can do it with our calculator, depending on how complex it is. You can see it almost looks like we have a point of inflection here in the middle. We actually technically don't. It is worth noting this is an always increasing function. If it's positive, if it's negative, it's an always decreasing function. However, this point here is a good thing to kind of consider when we're doing our sketch. It's going to help us with actually just putting our pen to paper and actually drawing this out. So let's jump into the actual sketching part. Everything else kind of does stay the same. If this is a 3, it makes it skinnier, but that doesn't really affect the sketch for a tan graph in the same way it does for a sine or a cosine graph. So you can see if I change this back to being just tan x, so my period's normal. Normally it would be at 0, and now it's going to be at negative pi on 2. So everything's shifted negative pi on 2 towards the left. So here's my function. I've kind of chosen a little bit of a more challenging one. The ones in the textbook over here I thought were a little bit too straightforward. So I thought let's do one that has a bit of everything as well. Now we don't necessarily need to do this in steps, but let's just put some steps out just to make our life a little bit easier and make it a little bit more methodical. The first step, as always, is to find the period. If I have a look at my function, you can see here that the coefficient of my x is actually 2. So just like in the example we did with the sine graph, I need to take a factor of 2 outside my function. That's going to give y equals 3 tan 2 outside of x. If I take a factor of 2 out, this is going to become pi over 4. Still minus 2, the domain is still going to stay exactly the same. Once I've done that, let's first find the period. In this case, t is going to equal. This graph's a little bit different. We saw with a sine graph or a cosine graph, it does one full wavelength in 2 pi. However, for a trig function, if I do my little trig graphs, these roots occur at every pi interval. So for my period for a tan graph, it's going to be pi over b, which in this case is going to be pi on 2. Which is what we saw in that Desmos example as well. Step 2 is going to be to establish the number of wavelengths. So let's figure out the number of wavelengths. That's going to equal final minus initial. Because I have negative pi, it's going to have a double negative all over pi on 2. That equals 2 pi divided by pi on 2. We can write it out this way to help with our manipulation of our fractions. If I have this, keep it, change it, flip it. Simplify. I'm going to have 4 full tan waves within my domain from negative pi to pi. Now, we don't really have critical points in the same way. We do, however, have x-intercepts. So let's just change this step into find the x-intercept. So if I want to find the x-intercept, I'm going to let y equals 0. That's going to give 3 tan 2x minus pi on 4 minus 2 equals 0. So now if I do some rearranging, I can add 2 to both sides. I can divide both sides by 3. I get tan of 2x minus pi on 4 is equal to 2/3. Now, I don't have any exact value for tan at 2/3, so this one is going to be something we will solve with our calculators. This would have to be in a tech active test. In order to get our solution, we can do a similar idea. If we did have exact values, we let theta equal to x minus pi on 4. We could do that the same way we did with our sine function earlier on a couple lessons ago. So once I've done that, then I also need to consider other things are important that are like, I'm just going to write middle or center point. And I'm going to figure this out using transformations. If it's normally 0, 0, and I've shifted by negative pi on 4. So it normally starts at 0, 0. I've now moved back pi on 4, and I've gone down by 2, which means this center point here is going to be negative pi. Oh, sorry, it is negative. So in this case, it's going to be plus. It's my bad. It's going to be plus pi on 4, comma, minus 2. So I just know what I'm going to do a sketch. I'm going to have some point around that coordinate. If it is around that coordinate value, I can just kind of do the rest of them around that point. So I don't actually need to mark these on my graph. It's just to help me, again, just visualize where this whole thing is going to sit. So once I've done all of that, my amplitude doesn't impact my sketch. My horizontal shift, I've kind of factored for here with the center point. I know my period. I know the number of wavelengths I have. I know my domain. So let's find our asymptote. And as a quick note, for some of our tan graphs, if it's a simple function like tan of 2x, for example, it might be an easier way because that's going to equal sine of 2x over cos of 2x. My asymptotes occur when cos of 2x is equal to 0. So it could be easier solving for cos 2x equals 0. That may be, for simple angles, that may be an easier way to find your asymptotes. However, for this question, because it's a little bit more complex, we have a 2 outside of x minus pi on 4. There's another way we can go about solving for this. But I just want to put this in a little box to say, hey, this can be an easier way to go about it depending on the questions. Let's put that little note over here in the corner. The way that we can do it for more complex functions is this idea. It is 2k plus 1 multiplied by pi all over 2 times b. In this case, my period is going to be b, which gives 2k plus 1 pi over 4. Now, what this k value here represents, we say this k is an integer. So k is going to be some integer, it's going to be some whole number. And essentially, we can just put points in to test. That's going to give us where we have asymptotes. So I need to consider my boundary conditions. In this case, my boundary conditions are between minus pi and pi. So if I consider my boundary conditions between minus pi and pi, where k is a whole number, let's just start at 0 and work our way in positive increments up till we reach positive pi. We get greater than positive pi. Because we have symmetry, I can then simply just, go the other way quite easily with that idea in mind. So if we look at this, if I just substitute for k is equal to 0, let's just start with the smallest number. If k equals 0, I'm going to have asymptotes. If k is equal to 0, then that's going to be pi on 4. So I'm going to have asymptote at pi on 4. If k is equal to 1, I'm going to have 3 pi on 4. If k is equal to 2, I'm going to have 5 pi on 4. And at 5 pi on 4, I'm already outside of my domain, so I don't need to worry about that particular point there. So that means I just go up to 3 pi on 4. Now, let's bring this across and do the negatives. 0 is going to stay the same. If I do minus 1, it's going to become minus 2 plus 1. That's going to give, minus 2 plus 1 is going to give negative pi on 4. And if I do minus 2, that's going to give negative 4 plus 1, which is going to give minus 3 pi on 4. So just know that these asymptotes work based on the idea that this would just be tan of 2x. Now, because I also have a phase shift and I'm shifting my whole graph by negative pi on 4 or pi on 4 towards the left, that means I also shift all my asymptotes by that same factor, which means in reality, when I'm doing this, I actually need to do one more either side because it might result in having another asymptote that falls within this particular boundary. So the one I had that I got rid of was the 5 pi on 4. This is when k is equal to 2. 2 times 2 is 4 plus 1 is going to give 5 pi on 4. Now, what I'm going to do now is I'm going to subtract pi on 4 from each of these asymptotes to get their new location after they've been phase shifted. So that's going to give negative 3 pi on 4 minus pi on 4 is going to give minus pi. That's going to give minus pi on 2, 0, pi on 2, and then that's going to give pi. So that's the location of my new asymptotes. I can now go ahead and draw my sketch. So there we go, a nice long axis like so. And I'm going to start by actually putting in my asymptotes because that's on my boundary condition, which makes the sketching a little bit easier. So let's just say this here is going to be at minus pi. Now I'm going to put my second one in. I'm just going to space it out nice and evenly because I can. 1, 2, 3, 4 gives me my second one here at minus pi over 2. Then I'm going to have 0, put that in a slightly different color. I'll go up another 4. 1, 2, 3, 4. 1, 2, 3, and 4. So there's my asymptotes. I worked out earlier that I already have a point. That's the point pi on 4. Pi on 4 at minus 2. That's going to be somewhere around about here. That's sort of the middle. Actually, let's put it on that line. Somewhere around about here on this line. So I've placed it there. Let's label this as well. Pi on 2, and this is going to be pi. So that means all my center points are going to be around the middle on that same line. And that's all I was really trying to establish, is just where is kind of the middle of my tan graph. Now what I do is I just draw my sketches like so. Again, these continue in all directions forever and ever. And that's all you really have to do. We should find these points here. I've chosen a bit of a messy graph, so just solve these on your calculator, get some weird decimals, label those, and then you are all done after we do the X and Y axis. Now we're all done. That's how to sketch any tan function. If you want to practice this process, like I said, there's 2 ones over here that are maybe a little bit more user-friendly, and there's some solutions as well to help you check.